Sure. Hello, everyone. This is the webinar for simulation results as part of the first level interconnect characterization for low temp materials. We'll be highlighting the phase 1 of this project that we've been doing for a couple of years now. So with that, I'll start the introduction. So project motivation was to evaluate low temp materials specifically for first level interconnect. In the past, iNEMI has looked into it for second level interconnect, BGA type, but we wanted to focus exclusively on the first level and the unique sense of challenges that interface takes. So the inspiration of this is to enable advanced packaging with lower processing temperatures. There's a lower stress to the package in general, done during an assembly, which leads to reduced warpage due to CT mismatch, lower thermal stress for sensitive components or sensitive materials that can't handle a traditional high temperature reflow. The end goal by having less thermal stress to the package is to hopefully increase package reliability. This is due to the reduced thermal excursions, as I mentioned, and then because of that, less thermal and mechanical strain. So with that, I'll go into a brief overview of the project scope. So this project consists of 2 phases to study this phenomena of low temp materials for first level interconnect. Phase 1, which is complete, it began with an industry survey to see the interest in low temp material and its applications across the industry. Next half of phase 1 was to conduct a modeling and simulation study to explore different aspects of interconnect. This was split into 3 different studies: solder bump collapse, electromigration, and thermomechanical. Those are going to be the bulk of the topic of today's webinar. Phase 2, which we are working on right now, is actually testing low temp solder versus traditional SAC solder on actual test vehicles. So this is a work in progress, and I have a slide about that later on in the presentation after the bulk content. Okay, so we'll go on to the project members. So the project leader is Shripad. He will be presenting the solder bump collapse section of today. I am Russell Kasberg, co-leader along with GPay, and of course our iNEMI leader is Surya-san. And we have other companies, Intel, IBM, Indium, Senju, Shinko, and Heritage that are also work with us on this project. So the next slide is package geometry. So for all 3 of these simulations, we targeted 2 different interconnect configurations. The dimensions here I'm not going to go into, but basically we looked for all 3 simulations at a C4 type geometry and a copper pillar geometry to look at fine pitch, future advanced packaging in our copper pillar, and then more traditional first level interconnect with the C4. So all these simulations use similar geometries throughout them so they can be, compared between each other. Next slide, I'm going to hand it over to Shripad, who will go over the solder bump collapse simulation.
Thanks, Russell. Are you guys able to hear me okay?
Yes, I can hear you.
Sounds good. Can I go to the next slide?
Hmm.
Yeah, so as Russell mentioned, the first objective of this particular program was to understand through simulations what are the effects of low temperature solder on variety of aspects, including solder bump collapse, as well as some of the mechanical, thermomechanical simulations that our other team members will go through next. So I will focus on the first aspect, which is the solder collapse modeling and effect of low temperature solder on that collapse behavior. So to do that model, the scheme that we used is what is depicted on this slide. So as inputs to the model, we are using geometry of the bump and the parameters that we used as the input parameters are listed here, which are the standard input parameters for a solder geometry for a first level interconnect, such as bump diameter, the height of the die bump, including solder height or the solder volume, and then the size of the solder resist opening, the SRO size, as well as the diameter, the depth and the diameter, which will control the overall shape of the given solder volume. And then the SOH is the solder standoff height. The way that is defined in this model is it's a z-directional height delta between the two metal planes. So in this case, the copper pillar as well as the metallization pad on the substrate. So that effective standoff height is indicated by the SOH. And then the bump offset here is a parameter, but for this modeling, we didn't have to incorporate since this was based on a just a solder collapse model for a typical system in a theoretical manner. As an output of this collapse model, what we're looking at are a few parameters. The first being what is the equilibrium solder shape, and I will describe in the next few slides during the data review what that equilibrium solder shape actually imply physically. And the other key output out of this collapse model is the risk of solder bridging. In other words, how much XY dimensional tolerance we have before, based on this model, before the solder is bulged so much so that it will connect to the adjacent solder and will bridge. So that's the solder bridging risk that we estimated based on this model output. And then the third key parameter as an output from this collapse model is during the bonding process, what is the effective compressive or the tensile load? And that also has an effect on the overall solder standoff height, solder wicking, and that bridging risk, as we'll go through in the next few slides. So that's kind of the overview of what the model does in terms of output and what inputs it takes. And then the bottom right picture there that is shown for the solder contact angle. So that was an empirical data that we collected across different sites to understand what should be considered as an effective solder wetting angle, which is one of the key modulators to the input, and then what is the effect of low temperature solder versus a conventional tin, silver, copper SAC solder on the overall wetting behavior. And some of the snapshots of the model that you see in the bottom left picture. So what you see is various stages of how the solder shape progresses as the top die starts getting closer and closer to the bottom substrate, and the solder goes through the entire collapse cycle, including wicking, the bulging, and then we studied this as an effect of few of the different parameters. So that's the overview of the model, and next few slides I'll describe some of the results which are based off of this idea of the model. Okay, next slide. All right. So as I mentioned, the first key input parameter that is critical to this model is solder wetting angle. And we wanted to compare that between low temperature solder as depicted in this top right side plot here under the name LTS, low temperature solder and a conventional solder. So to do this, the methodology that we used at 3 different site locations to get measurement variations incorporated are used using an optical methodology, and the depiction of that optical methodology is shown in that middle picture there with the 9 mil sample and the 24 mil. The 2 different solder shapes that you see, or the solder sizes that we see, 9 mil and the 24 mil, was specifically used to just understand any impact of the overall solder volume on this methodology. Expectation is the solder contact angle at equilibrium is not dependent on that actual diameter of the solder, but rather is dependent on how we measure. So we wanted to incorporate that variation in the measurement. And then we looked at the range of the contact angles and looked at the wetting behavior. Along with just the contact angle, we also looked at 2 other parameters to better understand the behavior of wetting, as shown in the bottom 2 pictures. The first parameter we also looked at is that diameter of the solder spread, and then bump height and the contact angle upon spreading. And all this data is collected on copper coupons with the same fluxing agent that was used across various measurement locations so as to confirm any variation because of the methodology itself. So this is an equilibrium contact angle of solder on copper coupons in the presence of flux after reflow and cool down to room temperature using optical methodology. And then the contact angle data that is shown on the right, what we wanted to understand was as a reference when we look at conventional SAC with copper plane, copper coupon, that measurement was around 43 to 45 degrees. So we wanted to see, in theory, the contact angle with the low temperature solder, is it different at all? Because that will become as one of the input parameters. And what we actually observed out of all these measurements at various data locations within a coupon to coupon, and if we combine all those variance components, what it showed is, although the range of the solder contact angle is of the order of 8 to 10 degrees from the reference mean, and it's lower than the mean contact angle is lower than the typical 43, 45 degree contact angle of SAC on a copper coupon. That was not the primary contribution because of low temperature solder itself. What we observed rather is that range of measurement errors because of wetting to the copper coupon, the fluxes, is more dominant factor rather than just the intrinsic delta between copper to conventional SAC solder and copper to low temperature solder. So then in the model, in the follow-up slides, what we ended up using was a range of this contact angle to get sensitivity because of this low temperature solder's contact angle behavior. So we use this contact angle as an input to study the sensitivity rather than to study it as a direct input parameter. So that was the key outcome of this contact angle measurement. Okay. Next slide. So to go a little deeper into that contact angle data, as I mentioned, when we plotted all that across multiple sites and compare tin bismuth which is one of the low-temp sorters that we consider in this project, versus the conventional stack sorter. What we actually observe is the surface metallization, the solder alloy, and the reflow temperature before we cool it down. Those became the key modulators affecting the solder behavior. The sample preparation and the associated measurement errors, they rank the wettability variation, and therefore then we use the range of these contact angles more as an sensitivity study in the subsequent modeling for the collapse. But the solder contact angle by itself is not the primary change because of low temp solder. That was kind of the key result out of this contact angle study. Okay, next question. Okay, so once we took that solder contact angle, the other model input in a conventional mass reflow process would be the warpage behavior into the overall collapse. So that warpage behavior, whether it's concave or convex, depending on various parameters such as the buildup of the substrate material, the relative temperature through the reflow cycles. So that is the other key parameter that would affect. For this purposes, we are assuming a uniform 10 by 10 die area at 130 micron pitch. So we assumed that warpage behavior is equivalent across different cases. And the bottom two snapshots out of the modeling, they are showing the final collapse. Some of the terminologies that we will see in the following two graphs is explained here. So the first key terminology is what we call solder bulge. So that solder bulge is the parameter that we are using as an output of the model, one of the outputs, to get a sensitivity to that bridging distance that you see with the red line between the two adjacent solders. So in short, if that solder bulging in the two consecutive bumps is in that concentric location to the extent that they approach that minimum distance, which is kind of half the CD between half the annular spacing as a relative parameter. If it approaches that red line, that's what will be considered as solder bridged in the model. So then we are tracking in the model as the top solder is collapsing on the bottom solder. How is this bulging extending? Now, the other thing that is happening that you will see in the model is along with the bulge, at certain point, based on the contact angle, the solder also rises on top of that copper cap, and the copper cap thickness is another key input parameter, therefore, to this overall collapse model. So we studied kind of two different ranges of that top copper cap thickness as well. Okay, next slide. So with that background on the collapse model, let's talk about what the collapse model actually showed. So on the top left, you see two cases there. One case, the case one is with the solder of a different geometry. The other case is the solder of a lower effective solder volume on the die side. So on the right side, you see two plots. So the first plot is the force. This is a reactive force as sensed by the head that will be holding the top die in a certain compression force or certain force and temperature as the solder is approaching, or the top head is approaching the bottom solder. Now, the way to understand this data is if you follow that top curve and follow that blue arrow from right to left of the x-axis. What that right to left as you go along the x-axis, that is showing the progression during solder collapse, meaning that in that time scale, right to left collapse is when top solder is approaching the base solder. The solder is collapsing in a controlled manner. Then the y-axis is denoting the force with which the the solder is putting as a reactionary force. For the convention in this model, the positive force is considered as the compressive force. The negative force is considered a tensile force. So as you see in the bottom picture, and follow that hourglass shape initial solder. So as soon as the top solder connects the base solder, at certain point in the Z collapse, the solder has formed this hourglass shape. Assuming perfect wetting, there is no oxide film remaining. So the solder has already merged and no oxide is preventing it from merging for the model purposes. Now, as the solder is getting compressed with the top head coming closer and closer to the bottom substrate, we are going along the right to left on this plot, both the force plot as well as the solder bulge plot at the bottom. As you see, initially, the force is the tensile force. If you follow the two sensitivity curves, blue curve for the 30°, the lower contact angle, the orange curve for the higher contact angle at 45°. What it shows is for both the curves, initially, they are essentially collinear. They're always on top of each other up to a point where the solder has reached an equilibrium bulge, or where the force has started to transition from tensile negative to compressive positive force. The effect of solder contact angle starts showing up to the left of that about 60 to 57°, 60 to 57 collapse for this geometry. What it's showing is when the solder contact angle is lower, so consider the blue curve, as you are going, maybe Russell, you can show with the cursor along that blue curve. As you're going along the blue curve, yeah, right there, you see the difference starting to show up between the lower contact angle or the 30° and the larger contact angle 45° case, wherein the transition from tensile to compressive regime happens much faster for the lower contact angle case than the higher contact angle case. So the lower contact angle case reaches that compressive regime much faster. Now, accordingly, if you follow that transition regime, or what we call the copper wetting regime, in the bottom plot, the solder bulging plot, what you see is that bulge of the lower contact angle solder, because it is not wetting on the top of, is easier to wet on the top of that copper cap, as is shown in that snapshot of the model. That bulge of the relative solder is higher for the lower contact angle versus the higher contact angle orange curve. But then as you keep compressing and keep going left, beyond, once it reaches kind of an equilibrium state, both of the curves again coincide and go along the same line, because that's when now the effective collapse is done. What's taking over is the solder geometry, not the wetting behavior. So the key summary out of this collapse simulation, what we saw is what is shown in the bottom two bullets. The first is, if we consider a low temperature solder, in theory, which should have a better wetting, smaller contact angle system, the transition to the compressive force with the low temperature solder is happening relatively quicker, and the bulge will be relatively more, or the propensity to bulge will be relatively more. And the other key takeaway from this is it reaches that tensile to compressive regime earlier. So physically, what that would imply is that relative solder bulge and the compressive load is higher than the poorer wetting or a conventional solder. What this would imply in the physical world is if one uses the low temperature solder systems for first level interconnect, then we have to design the solder geometry to take into account this faster wetting and the faster collapse behavior of the low temperature solder. That's the implication out of this model for physical kind of process. Next slide. And then this slide shows what would happen if you now take a lower solder copper cap height. So if you look at this slide, the copper cap height is 30 micron. If you just go back to previous slide, Russell. The copper cap height in the previous slide was 12 micron. So now what you will see in that next slide is everything else being the same, just increasing the copper cap from 12 micron to 30 micron. One can now imagine it's little harder for the solder to rise up for the same effective contact angle. So effect of this low temperature solder or the faster bulging system on joint formation is more pronounced at relatively taller copper height because it's just going to bulge more. So that's what the plots on the right side show, the relative bulge of this 30 micron copper cap system versus the 12 micron for rest of the solder volume, etc. being the same. For the low temperature solder, that bulge is much higher. So what this would imply in the physical sense is when one starts to go into these low temperature solder applications for first level interconnect, not only this solder contact angle and the wetting behavior that needs to be comprehended in the interconnect geometry, but rather we also need to comprehend the copper height design, which also has then implications to the electromigration as well as some of the other electrical parameters in the whole first level interconnect architectures with low temperature solder. Okay, so last slide. And this just shows a over kind of exaggerated version of what happens when this collapse is happening and what is happening because of the actual physical contact angle differences in a depiction to explain it a little further. So the effect of contact angle on the low temperature solder is not significant contributor to collapse, but rather it becomes more and more pronounced with the increased copper pillar height. Okay, next slide. So with this collapse model simulation, the key takeaway was for the first time, we are able to then demonstrate the effect of low temperature solder on the dynamics of this joint formation. And all these length scales that you saw on these plots are in the time sense are happening at millisecond level during the joint formation. So if one cross sections the final joint, you might or might not even see these differences. You will see the effects in the final yield or the sort of bridging or opens. But when one dynamically is able to zoom in within the millisecond level time scales during the joint formation, that's what this model tried to capture, which was the key takeaway and the uniqueness of this model to extract the behavior of low temperature solder. And then this learning is then critical to, as I said, not only joint formation, but then designing the right geometry, the copper pillar heights, solder volumes, which have implications to electromigration and the other reliability modes for the low temperature solder systems. In the next few slides, our team members will go through some of the other thermomechanical simulation now. Okay.
So next simulation will be covered by Moriyama-san on electromigration.
Can you hear me?
Yes.
Okay, next slide, please.
Okay.
Here's today's agenda. Firstly, we introduce background on electromigration evaluation. Secondly, simulation model dimension description. Then I'm going to explain simulation result. Finally, conclusion for our activities. Next slide, please. So, with a minimization of bump pitch, the current density of which bump is on the order of 10 kA per square centimeter. It is very important to have a better understanding of electromigration in flip chip joining. Electromigration is a phenomenon caused by electron flow. The electron flow causes mass transfer from the cathode to the anode side. As a result, void work from cathode interface. Typically, a failure occurs on the cathode side. Next slide, please. Electromigration concern when using low temperature solder materials. In general, material with a higher melting point and higher modulus are less affected by diffusion. This table shows the electrical resistivity and Young modulus of each material. Low temperature solder materials such as tin bismuth solder tend to induce electromigration. Next, please. Here, so the relationship between current density and the electromigration lifetime. This graph is a general relationship derived from Braggs formula. If the current density 2 doubles, the lifetime is reduced by approximately 1/4. Therefore, in this study, the difference in current density distribution between SAC 305 and tin 57 bismuth compared. Next, please. Here we show the difference between SHC and tin bismuth system electromigration phenomena. Left figure shows the SHC 305, right figure shows the tin 57 bismuth solder. So in case of SHC 305, tin atoms migrate to anode side by the electron flow. However, the metal atoms hardly move by the backflow. Open failure occurs between solder pad interface. As a result, a rapid increase in resistance occurs. On the other hand, in case of tin bismuth system, bismuth atoms migrate to anode side by the electron flow, and tin atoms migrate to cathode side by the backflow. Also, a rapid increase in resistance is observed in the early stage of the electromigration test. However, no open failure is observed. So, therefore, we added analytical model of bismuth plus tin in separate model. Next, please. We employed 3 analytical models. One is SH305, center tin 57 bismuth. Right figure shows the bismuth plus tin models. Next, please. This slide shows the analysis conditions. We applied 3D model, and the current density is 40 kA per square centimeter. This value is defined as smallest opening area of solar resistor. And in this study, IMC formation and the Joule heating effect are not considered. Next, please. Here are the material property used in the electrical field simulation. Particularly noteworthy, the electrical resistivity of bismuth is approximately 8 times that of SAC 305. This difference affects the current density distribution. Next, please. This slide shows the result of current density distribution. Left figure shows the result of SAC 305. Center is tin 57 bismuth, and the right figure shows the result of bismuth plus tin. So maximum current density was simulated on the chip side of the SAC 305. In case of tin 57 bismuth, current density on the cathode side is lower than that of SAC 305. When bismuth is migrated to anode side, the maximum current density appears at the solder copper interface on the sink side. Next, please. This graph shows the current distribution in each slice place of the pump. blue line shows the chip side interface, and line 1, and line 4 is the part side interface. So regarding SSC305, current distribution is from sink portion to source portion. In case of TIN 57 bismuth, gradual distribution on cathode side, and the peak value is observed at the solderless edge portion. In case of bismuth tin, peak value is observed at the sink portion. This value is higher than that of SSC305. Next, please. This graph shows the current density distribution in the slice 1 and 4 of each model. Regarding to line 4, SAC305 and bismuth plus tin show almost the same trend. This is expected to be influenced by the electrical resistivity of tin, the main component of solder. Regarding line 1, in SAC305, the current density increased rapidly toward the source portion. These results indicate that the tin bismuth system may have low current density concentration during electromigration test than SAC305. Next, please. Conclusion. Maximum current density of homogeneous tin 57 bismuth interconnect showed lower than that of SH305 interconnect. Electromigration of bismuth shifts the location of maximum current density from die path to copper path. Using tin bismuth solder has the potential to lower than current density than SH305. Okay, that's all.
Okay, thank you, Moriyasu-san. And our last simulation review is by Mara-san, who's going to be covering the thermomechanical analysis. So.
Okay, good morning, good evening. Can you hear me?
Yep, we can hear you.
Okay, thank you. Move on next page. Okay, here is today's agenda. Firstly, I introduce the project overview briefly, and secondly, simulation model dimension description. Then I'm going to explain simulation case and result, and finally, conclusion of our study. Okay, move on next. Yeah, for the as Russell explained before, for this iNEMI project is a low temperature material we call the LTM, the discovery and the characterization for first-level interconnect. There are following advantage such as minimizing effect of the substrate warpage and the CT mismatch during bonding, and allowing heat-sensitive component, and lowering carbon footprint. And there are two. We are planning two phases about the tin bismuth solder based on the LTM for first-level interconnect. And today I introduced the phase 1 simulation, especially some mechanical characterization. Okay, move on to the next page. Here is the objective of my study. There's some mechanical analysis by FEM for tin bismuth and tin silver copper, we call the SAC, so the joint in the 2D package during a temperature cycling test. In elastic strain range per cycle, that is a factor in solder fatigue for the joint. And we did 2 geometry and 5 solder materials difference. I will explain detail of each simulation case in the next session. Okay. Move to the next page. Yeah, here is a simulation package overview. Laminate size is 37.5 by square and 10 millimeter square the silicon chip. And as Lasse mentioned before, we using two type of the solder bump structure. One 30 micron pitch C4 bump, and another is a 40 micron pitch caterpillar type. Actually, in reality, the substrate and underfill change for the fine pitch caterpillar bump compared to the C4 bump, but in this simulation study, the same substrate and underfill are used for the 40 micron pitch and 130 micron pitch to see the effect of the solder joint. Okay, move to the next. Here's a FEM model description. We are using a global and submodeling method, and the quota model is used for the global model. In case of 40 micron pitch bump, model size are huge size to obtain the results. So therefore, only a 10 by 10 bumps at the chip corner are modeled. For others area, caterpillar, solder, and underfill are modeled as a composite material. The composite material doesn't include the plasticity property. And the submodel, we call the micro model, including one C4 and caterpillar joint, is used for the location with the largest solder strain in the global model. Okay, move to the next page. Here is a material property that we used for this study. We said that two types of SAC and the three types of the thin bismuth were used for analysis. We are selecting existing another parameter for non-linear analysis to get a fatigue factor such as an accumulated in elastic strain and accumulated plastic work density. If you are interested in each material property more detail, please refer the attached reference document. Okay, move to the next page. Here's the temperature profile of our simulation result. Basically, we use for the JEDEC standard temperature cycling. And stress-free temperature is a little bit different of the SAC and thin bismuth. And also, underfill material is curing during cooling from the reflow profile. Okay, so move to the next page. Here's a sample of the simulation result of the accumulated in equivalent in elastic strain of the C4. Firstly, we evaluated three sections like light figure near chip side and near solder rigid surface and then near laminate copper pad. We selected for the element volume average calculation of accumulated equivalent elastic strain. Before the temperature cycling, like a cooling and the early phase, the section near the chip side shows the highest accumulated in elastic strain for SAC. However, after the temperature cycling, the section near the laminate copper pad shows the highest. So for the thin bismuth, near laminate copper pad is always highest. Okay, move to the next. Here is a caterpillar result sample of the SAC and tin bismuth case. This is we selected the two sections near the chip, silicon chip side and near the laminate side. As a result, we selected the near silicon chip side was selected for the SAC and the tin bismuth. Okay, move to the next. Here's the contour image of the accumulated in elastic strain at the minus 40 degrees C in third cycle as shown. Maximum point of the contour appears near the laminate side for the C4 and the silicon chip side for caterpillar, as I mentioned before. Okay, to next. Yeah, this is a summary of the normalized accumulated in elastic strain per cycle at third cycle. This result normalized based on the SAC 305 type A for each geometry. These results were obtained near the laminate copper part for C4 and near the silicon chip for caterpillar. The tin bismuth is lower than that of the SAC, even the geometry difference. Okay, to next. Here is a contour image of the accumulated plastic work density. And the maximum point of the contour appears near laminate side for C4 and silicon chip side for caterpillar as well as in elastic equivalent strain. Okay, move to next. Here is a summary of the normalized accumulated plastic work density per third cycle, end of the third cycle. These values also normalized based on the SAC 305 type A as well. The result is almost same as in elastic plastic strain. Okay, move to next. Here overall result summary for geometry and material. Accumulated in elastic strain range and plastic work density of caterpillar is higher than that of the C4. And also accumulated in elastic strain range and the plastic work density of SAC is higher than that of the tin bismuth, even many type of the difference. And it was more than twice, but it depends on the material type due to the difference of the another parameter definition. Okay, move to the next page. Yeah, conclusion for these studies are we investigated some mechanical characteristics of tin bismuth and the SAC 305 solder joint for 130 micron and 40 micron pitches. Accumulated in elastic strain range and plastic work density of 40 micron pitch caterpillar is higher than that of the 130 micron pitch C4. And interconnect strain is a result of the thermal stress and is affected by bump geometry. Tin bismuth solder appears is to lower the overall in elastic strain and plastic work density. Tin bismuth accumulated less in elastic and plastic strain as compared as a SAC solder material. Okay, that's all for the thermal mechanical simulation.
Thanks, Yamada-san. So as I was talking in the beginning of this webinar, we are now on phase 2 of the project, where we're doing a test vehicle evaluation. So current status is we have our test vehicles assembled. we have a split between two different solder materials, that being eutectic, tin bismuth, and SAC being our control, and the interconnect being a copper pillar type. For stressing, we're undergoing thermal aging, ATC stressing, thermal shock, and electromigration. So with ATC and electromigration, we'll be able to correlate directly to the simulation results you have just seen. So that data will be upcoming. And then final summary is that the simulation results conclude that a low temperature solder material can be viable for the first level interconnect. We did not see any really giant red flags indicating that it wouldn't be viable for this interconnect. We are going to compare the simulation results with the phase 2 of the project that's undergoing now and hope to correlate with our simulation. And with that, we have a little bit more time. We're going to go on to Q&A. So if anybody wants to ask a question, come off mute or wave your hand or raise your hand. Answer questions. Okay, yeah, I see one hand raised, so you can come off mute if you want.
Hi, this is Ren from Silicon Connect. Yeah, thank you for the presentation. It's really good. So I have a question. I might have missed the background, like for LTS, how much lower the reflow temperature that we can go. And the second part of the question is, does it help to further push the bump pitch that we can do in reflow? Yeah, thank you.
Yeah, so for the eutectic solder or tin bismuth material that we're looking at, that has a reflow temperature around 130 C, as compared to SAC, which is 217. So quite a bit lower temperature difference. I didn't really understand the second part of your question.
Yeah.
Pushing bumps?
Yeah, the bump pitch. So I think lower reflow temperature usually we associate with warpage, and bump pitch limit is somewhat related to warpage as well. So I was just wondering that if now we can reflow at a lower temperature, does it also mean that we can use reflow for even smaller bump pitch than before?
Yes, I think that could be enabled. Again, you mentioned the warpage. Also, on cool down post soldering, we have less of a CTE mismatch, so there's less strain. So if the interconnect is smaller, it can withstand the that less of a thermal stress on it. It can withstand the smaller interconnect can withstand that better. So I think it could be enabled.
Okay. Yeah, it just if that were to happen, that means in some industry might not have to invest in TCB, which is a higher cost, and we can actually extend the usage of the reflow, which is which is why I think this project is also really valuable in this sense. Right. I mean, it'll be great in future if you have a more concrete like roadmap or how much quantitative, how much bump pitch is going to work. Yeah, thank you.
And one thing to add to what Russell said on the second question, yes, because of the low temperature solder, the overall temperature needed to reflow the joint and form the joint is lower. Thereby, one can deduce that the overall warpage of the system is lower, and therefore we can, in theory, enable lower solder bump dimensions, therefore smaller pitches. However, the flip side then is with the lower temperature solder, the acceleration of the solder consumption during the joint formation and subsequently upon reliability cycling is also faster. So the IMC formation and therefore the consumption of the solder in the system is faster, which can negatively affect the margin one would have as you go down in the pitch and therefore the solder dimensions. So to understand that effect, therefore, we are doing this second part of the project, which is understanding with reliability cycling, how much margin either we lose because of the low temp solder systems for the same equivalent temperature cycling or the bake cycling. So that would be crucial data then to kind of put this together and say, yeah, we can buy some margin with the low temperature solder, maybe with some caveats about what it means to the reliability cycling. So,
Okay, thank you. Yeah,
yeah.
thank you for the insight. Always nice to hear your voice again, Sripad.
Yeah, nice to see you. Thank you.
Yeah.
Can I also have the comment, Russell?
Sure.
Actually, that was a good comment from Ray Chan. Always you have very good ideas and comment. Thank you very much, Ray Chan. Probably, as you mentioned, that we might invest more about the possibilities of the C4s or copper pairs versus the TCVs. How those traditional technologies can get the benefit in terms of the TCVs using the low temperature materials. So, and also how much we can, reach to the more fine pitches because of the lower operational mismatches. That's probably we might consider at the next step. So I would like to contact with you, so Rachel, when we will work on next phase.
Yeah, definitely. Yeah,
Thank you very much.
Tsuruya-san.
Yeah, thank you.
Thank you.
We have 1 minute left. Does anyone else have any last questions before we wrap up the call? Okay, I think that's it for questions. So thank you everyone for logging on to the webinar today, and hope to catch you when we are done with phase 2 with the results from that. Thanks.